Hi guys, welcome back again. This is the second video. We're going to cover the next six functions. And sorry if I'm talking fast. I had too much coffee this morning, so I'm all amped. I don't always drink coffee too, I think, so I have like it affects me more than the average person. Okay, so anyways, here's a cube root function, the reciprocal function, reciprocal square. Reciprocal just means it's 1 over the value, right? Reciprocal square means 1 over with a square. And then we got these two rational powers, which these guys, to be honest, I don't necessarily have these already memorized. The rest of them I pretty much have in the back of my mind what they look like. These ones I don't have memorized, but even if you don't have them memorized, then they're not hard to deal with. You just do the same thing we always do and just kind of think through it, plot a couple points. And then lastly is the greatest integer function, which is also called the step function. Or a step function. Step functions, there's two types. We're only covering the greatest integer function today. And let's keep it that way because when you have both of them, it starts to get confusing. So greatest integer function, and then you'll come across the least integer function at some point in the future, I think. And I guess I'll briefly mention it, but we're not going to cover it in detail. The book doesn't cover it either, so. Okay, let's start with the cube root function. So it's kind of similar in a way to the square root function, right? Here's a square root function. Looks like that one side. The cube root this time, this right side looks similar, right? Just kind of a little shorter, but same general shape. But then this time you also get the left side. Why do you get the left side? Well, you can take cube roots of negatives because a negative times a negative times a negative equals a negative. Which means if I have something like the square root of -1, I can actually get an answer. That is -1, right? I'm sorry, cube root, I mean. If I take a cube root of -1, I get -1. Why is that? Because -1 times -1 times -1 is equal to -1. Or another one I could take is I could take a cube root of -8. Because what's the cube root of -8? That would be -2. -2 times -2 times -2 is equal to -8. 248, right? All right, let's say you don't remember. So what are you going to do? Same thing we always do. Just plot some useful values. And honestly, if I ever graph one of these, I do still make the table anyway. Even if I know the general shape, unless I just want like a super general graph, I still make the table just to help me plot it more accurately. So which points I always will pick is 0, because the cube root of 0 is 0. 1, the cube root of 1 is 1, and so -1 is also -1. We just did -8 was -2, right? And the cube root of +8 is +2. So I got all those points. Let's plot them. 0, 0, 1, 1. Okay, I don't know. You guys look like you're a little off in your picture. Or maybe their 1 is actually here. Maybe they're doing half, looks like. Yeah. Maybe these are scales of 2. Okay, -1, -1. -8, -2, 1, 2, 3, 4, 5, 6, 7, 8. -1, 2. 1, 2 would be here. So yeah, that actually looks like it matches better. And then +8, 2. 1, 2, 3, 4, 5, 6, 7, 8. 8 is right here. And then 1, 2 right there. So yeah, beautiful. There you go. Looks like these are increments of 2. So 3 would be here like that. Yeah. Okay, so that's the picture of it. Looking at it, once I have my picture, it goes on to the left forever, on to the right forever, with no breaks. So the domain is everything, -infinity to +infinity. Same with the range. I know it's hard to tell when you look at the graph because it looks like it's not going to go very far down. But if you continue long enough, forever and ever, this is eventually going to get really, really big, right? And really, really big in the negative direction as well. So that means you have all values, positive and negative for the range as well, up and down. Now it's increasing the whole time because as you read from left to right, it never starts going down, only continues to go up, right? So always increasing. And this one's got odd function symmetry because, well, this is an odd root, right? Odd root. And also, I guess, it works for the odd roots. I know the even root over here, it did not have symmetry. That's because you couldn't have the bottom half, right? If you had the bottom half too, then you would have had even symmetry. but because oh no, I take that back. That's not even true either. Yeah. So even ones don't have any type of, even fractional powers don't have symmetry. But the odd power does have symmetry, right? And then why is that? Because if I was to rotate this 180 degrees lands back on itself. That's the cube root function. Okay, next is the reciprocal function. One that I think often kind of goes unnoticed when you're learning a bunch of graphs and stuff. So I'm glad they included it here because it is a pretty important one, and one that is kind of surprisingly curvy. Because when you see like just, it seems like just a single x, you might think, oh, shouldn't that be like a line? But if you think carefully about it, actually it is going to have this kind of curve to it. Now, let's try to plot some important points like always. Let's say you forgot how to graph this thing. This is y equals to 1 over x. I just repeated myself twice. Okay, so if I plug in a 0, then I have 1 over 0, right? Which is undefined. That means you have a vertical asymptote right here. That means that this value is impossible, right? It's an undefined value, so that this center line is never touched. There's no value for the function. It's not defined there. Now, what happens if I go just 1 out? If I go 1 out, 1 over 1 is 1, right? If I go 1 to the left, -1. 1 over -1 is -1. What happens if I go to 2? Well, I get a half, right? If I go to -2, I get a -half. So let's plot what we have so far. So we know it's undefined at the center. 1 is a value. If I go to 2, it's at a half. If I go to -1, it's -1. -2, -1/2. So you see the pattern, what's happening as this number gets bigger, then you're getting closer and closer to 0, or you're getting smaller and smaller fraction. So that's curving that way. What happens if I put in a fraction? What happens if I put in like a half? Well, what is 1 over a half? 1 over anything, it just flips it upside down, right? So if I have 1 over 2, a half, it's going to flip upside down and become 2 over 1. Same thing with -1/2. Flip upside down, it becomes -2 over 1, or -2. So 1/2, comma 2 is another point. Here's 1/2, 2, right there. And you see it has the same shape on both sides, right? Here's kind of like the starting position. And it goes same shape on both sides of that starting position at 1, 1. Or -1, 1. The other part was -1/2, comma -2, right? That's right here. Okay, so another thing that you just want to have memorized is the general function for 1 over x. It looks like this curve. And 2 things to note here. It approaches this asymptote, so it gets super, super, super close to it, but never actually touches it. It goes up forever. And then it gets super close to right here, this horizontal asymptote as well. This line is going to get closer and closer to 0, but never quite touch it. This line is going to get closer and closer to 0, never quite touch it. This one continues on getting smaller and smaller, but never quite touches that center line. Okay, let's talk about domain and range. Domain, to the left, you get every x value, right? So -infinity up until 0. But we don't include 0 itself because that's undefined. So all this work is just to exclude that 0. So -infinity up to the 0, plus 0 onwards, but we have the open parentheses by the 0. Okay, the range, same deal. You're going from as low as you want up until the center value. You don't have anything where you equal to 0. And then from the center value on upwards, you get everything up high. So that means you have -infinity to 0 and from 0 to positive infinity. Okay, now where are you decreasing and increasing? Decreasing means you're going to be going down, right? And okay, this is getting messy, so let's clear all this stuff. We already figured out how to graph the thing. We plotted our points. Now we're just focusing on examining that graph we had and how do you determine whether it's increasing or decreasing. Well, if I leave it from left to right, it's going down this whole time from -infinity all the way towards 0, right? Okay, And then from here, also it's going down the whole time. It's never getting up as you read from left to right. So decreasing, decreasing, decreasing actually the whole time for the domain that it's got. So if you look, the domain matches the interval where it's decreasing. Now this one is odd because if I was to rotate this guy, it lands back on itself, which is kind of a beautiful thing if you think about it. All right, now the reciprocal square function, kind of similar to the reciprocal function. If I look at this portion right here, it's got the same general shape, right? I mean, the only small little nuance difference is it's gonna just reach all the points faster. So it's gonna get closer to this center faster, closer to the origin faster. Not the origin, but this line equal to 0 faster. But general shape, same. Now, what happened to this guy? Why is it on the top? Well, it's pretty much the same shape, but this guy got moved to the positive side instead. Got flipped over the x-axis because squaring makes things positive, right? So whereas this one was negative, because this is squared, it's flipped up there to now it's positive. Again, if you're not sure what to do, let's make a little table of values. 0, again, it's 1 over 0 squared, which is 1 over 0, so it's undefined. Again, you got the asymptote right in the middle. If I get 1, it's 1 over 1 squared, which is 1. Negative 1, it's going to be 1 over negative 1 squared, which is still positive 1. Oh, this is getting messy for some reason. Let me just switch to pen. So still positive 1. So that means I got positive 1, positive 1. I've got negative 1, positive 1. Right? That's kind of like the starting spot. And then just like the 1 over x function, from there it's going to have the sort of same shape going upwards towards that asymptote and downwards toward that asymptote. But you could put another point in. Let's what's a good one to check that I can take a square root? Well, 2. If I plug in 2, I'm going to get 2 squared. I'm sorry, I meant 1 over. I forgot to write that 1 over. 1 over 2 squared is 1 over 4. If I plug in negative 2, 1 over negative 2 squared is also 1 over 4. So at 2, you're at a fourth. At negative 2, you're at a fourth. Okay, what happens if I plug in a half? I got 1 over a half squared, which is 1 over a fourth, which is 4. What if I plug in negative a half? Well, I get the same result. 1 over negative a half squared is 1 over 1/4, which is 4. So at 1/2, I'm at 4. 1/2, 1, 2, 3, 4, right there. At negative a half, I'm also at 4. So right there. Yeah, so there's your picture. Okay, now once you get the picture, domain range is pretty easy. Domain, again, similar to the reciprocal function, all the way to the left, up into the center, but don't include that center. And then from the center, all the way to the right. Range is from 0 to infinity, just like it was. Oh no, I'm sorry, not just like it was. So it's only the top half that I can get, right? So I don't get quite to 0, but I can get everything upwards from there. So not including 0, that's why this is an open parentheses, and then upwards forever. Now looking at where it's increasing, decreasing, let's clear out this stuff so I can see it more clearly. Increasing, decreasing, as I read from left to right, it's going up from negative infinity up to the 0, right? So negative infinity up to 0. And decreasing from that 0 point where x is 0 onwards after that, it's getting smaller and smaller and smaller. So decreasing from 0 onwards. This is an even function because if I was to flip this over the x-axis, it lands back on itself. All right. Okay, those first 3 took a while. But yeah, it is what it is. These next 2, like I was mentioning before, these are not 2 that I personally have the shapes memorized in my head, but that's not a problem. We kind of just think about what's going to happen, right? Think about what's going to happen. Now, one thing I would like to point out, though, is the way they wrote this as rational functions. really the way that you want to think about these is like what I have written down here. So x to the 3 halves, that means it's a square root. See, the bottom number is the type of root it is, and the top number is the type of power it is. So this is really just the square root of x and then taken to the power of 3. So you do those two things. So now let's go on to make a little table like we do. First of all, and I'm going to write it like this, the square root of x to the third power. Can I put a negative number in? To do that, I'd have to take a square root of a negative, right? And that's not possible. So no negative x values are allowed. And that matches our domain here, right? I can't put anything negative. What if I put in 0? Okay, 0, take the square root of 0, that's 0, and then cube it, I still get 0, so that's no problem. 1, square root of 1 is 1, cube it, still get 1. Okay, now after that, I want to pick values that I can take an easy square root of. So the next value that I would want to pick would be 4. I can take the square root of 4, that's going to be 2, and then I cube it, I get 8. Right? So I get 0, 0, I got 1, 1, and I got 1, 2, 3, 4, comma, 1, 2, 3, 4, 5, 6, 7, 8. Right there. Okay, can't go to the left, right? Because can't take negative square roots. So there's. Looking at my graph, from 0, yes, onwards to the left, to the right. That's my domain. Range is from 0 upwards. That's that. Increasing the whole time of the graph, so matching the domain, except remember, increasing intervals, we have the open bracket or open parentheses. And it's neither odd nor even, because if I was to reflect it, it doesn't land on itself. And if I was to rotate it, it doesn't land on itself. Okay, so that's it. Rational power, that's the first type. Second type, similar. Again, you know, even though I say I don't have these guys memorized, once we start to deal with them, we see they're not so bad, and we see that the whole process looks very similar to the ones that we do actually know, right? Okay. I'm looking for a good spot. I'm going to write my table to the left this time because that's where I have more space. Okay, so one thing to know. Okay, remember, top is the power, bottom is the root. So this is the cubed root of x taken to the power of 2. That's what I have written down here as well. So what are some easy numbers? Well, 0 is always easy. Cube root of 0 is 0. Square root is 0. Then I want to pick something else that can take a cube root of. 1 and negative 1 are always good choices. The cube root of negative 1 is negative 1. And then when I square it, I'm going to get a positive 1. The cube root of 1 is 1. Square it, I get a positive 1. Okay, what else can I take a cube root of? 8 is the next one. That's easy. The cube root of 8 is 2 because 2 times 2 times 2 is 8. So 8, the cube root of 8 is going to be 2, right? And then after that, I take a square, I get 4. Negative 8, same thing. It's going to give me the cube root of 8 negative 2, but then I square it, I get positive 4. So I got 0, 0, 1, 1, negative 1, positive 1, 1, 2, 3, 4, 5, 6, 7, 8, comma 1, 2, 3, 4, right there. And negative 1, 2, 3, 4, 5, 6, 7, 8, positive 4, right there. And then we see that the graph is positive the whole time. So that means the range is going to be positive. Domain is negative infinity to positive infinity, right? Forever to the left and right. Range is, like we said, 0 to infinity. Decreasing, as you read from left to right, decreasing up until you hit the middle. And then after that, it starts increasing. So decreasing up to 0, increasing after that. And it's got y-axis symmetry because if I reflect this over the y-axis, it lands back on itself. Okay, guys, that brings us to the last function of the day. Let's take a breather here. And if you haven't been doing this, I recommend just, pausing the video whenever you need to take a 30-second break just to refresh your brain. They've done studies that show taking little breaks helps your memory, even if it's just for 30 seconds. If I was watching this class, I'd probably watch it at 1.5 or 2 speed and then take lots of breaks. But, it's up to you how you want to do things. Okay, this is the greatest integer function. A couple notations for it. So this is the one that the book gives. Greatest integer function also has this notation alternately down here. where it looks like instead of having the brackets completed, they just have the bottom side. Sorry, it's the bottom side with the extra line. Or another alternative notation is sometimes they just write a single line like this. Now, if you look at this notation, this alternate notation, it's kind of, to me, a good intuitive notation because, sorry, let me take a break. This is getting distracting. I want to erase all this other stuff. Okay, this notation that I just wrote, I think that's intuitive because it stands for the floor function. Floor function meaning whatever you input into the function, the output is going to be below it, or at least less than or equal to. Okay, now what the heck is the floor function or greatest integer function? Two different names for the same exact function. Well, it's the function that spits out the greatest integer that's less than or equal to the input. To me, this wording, I mean, it's necessary. I see why it is the way it is, but it's a little bit tricky because when you see greatest, your first thought is, oh, it should be something that's big, right? But that's not actually the case. It's the biggest thing that's still less or equal to. So let me give you some quick examples. Okay, this is, let's say I plug in, sorry, I want a pen. Let's say I plug in an integer. Let's say I plug in 1. If I plug in 1, what pops out? 1. If I plug in 2, what pops out? Anytime you plug in an integer, it just spits that integer right back out at you. Okay, so integer is easy. If I look at the graph, I've got all those integers, right? If I plug in, it's a 1, 1, 2, 2, 3, 3, negative 1, negative 1. So that part is easy. Okay, now what happens if I plug in something that's in between? So what happens if I plug in 1.5 into my function? Well, the function is going to spit out something that's less, but the biggest integer that's left, less, so that would be 1. What if I plug in 1.1? Also 1. What if I plug in 1.9? Well, I need an integer that's less. It's going to be 1. Why not 0? Well, 0 is not the greatest thing that's less or equal to. Okay. Here are a couple more examples. What if I plug in pi into this greatest integer function? Well, pi is 3.1415 blah, blah, blah. But it's 3 point something. So the biggest integer that's less is going to be 3. Right? If it's an integer, spits out the integer back. If it's not an integer, it's the biggest integer that's less than. What about 0.2? So 0 point something. Well, the biggest integer that's less than 0.2 would be 0. Now negatives, a little trickier. Still the same idea. Let's say I put negative 1.1. Well, I've got to have something less. So your first thought might be, is it negative 1? But no, because negative 1 is actually bigger than negative 1.1, right? So if you're negative, you go into the next integer that's less, so it would be negative 2. What about negative 1.7? Also negative 2. What about negative 0.3? The output would be negative 1, right? Negative 1 is smaller, and it's an integer. Okay, so that's how the greatest integer function works. Now let us plot some points. First thing to plot are the integer values. So that's really easy, right? Negative 2, negative 1, 0, 1, 2. If I plug in an integer, the output is the integer back again. So that's these closed .cc. Easy, 0, 0, 1, 1, 2, 2, 3, 3, like that, yeah? And then I'm just to get a feel for things, which side should I shade? Which side should I continue on? I'm going to plug in a fraction. So what if I put in 0.5? Remember we said the output should be 0. So 0.50 is right there, right? What about negative 0.5? Or negative a half? Well, next one that's less than negative 0.5 would be negative 1. So negative 5 would be negative 1 down here. And so you get this thing, no matter what integer you put in, let's zoom in a bit. I'm sorry, no matter what value you put in, if I'm between 0 and sorry guys, let me clear this up. So if I'm between 0 and 1, it's always going to spit out the biggest integer that's less than that, so it's going to be spitting out 0, right? So that's why I get this. Why is there an empty hole here? Because, well, once I hit to 2, then the function says I should go all the way up to 2, right? So I suddenly take a jump. And so what you see here is you have all these little steps. You have all these little steps. That's why it's called a step function, also called, in this case, the floor function, also called the greatest integer function. So different names. Okay, now, what is the domain? The domain is an interesting question. Domain is everything, because I have a spot where x is equal to every single value, right? It looks like there's a hole here, but it's okay because that hole is covered at the next jump. So I have every possible x value inputted. Now, what are the possible y values? So domain is everything. Well, the y values that are possible are only where there's a y value, or horizontal line, right? So I only have those integers. The integers are only possible outputs. So the range is the set. So yeah, if you have the dots means you go on forever. You could have -4, -5 as well. -3, -2, -1, 0, 1, 2, 3. And then dots mean you could go on forever and have 4, 5, 6, 7, but only the integer values. Neither odd nor even symmetry, because this one, if I was to reflect, does not land on itself. If I was to rotate, it looks like it might, but what happens that throws it off is these guys would have switched if it was rotated. So you don't have either type of symmetry. Okay, now I took this from the book. What they're missing is increasing, decreasing, or constant, right? Now, looking at this thing, it's never decreasing, never increasing, but there's lots of instances where it's constant, right? It's constant in all those intervals. So constant on all of those individual intervals. What are those individual intervals? Let's just pick one. So like here, that's from -1 to 0, right? But not including the boundaries. Union from 0 to 1. Union from 1 to 2. And onwards forever. And onwards in that direction as well. Okay, so that's it. That's the greatest integer function. All right, that's it, guys. Finish our 6 for this video. All right, we'll start tackling the problems in the next one.